lab, show you what I was looking for calculations and answers. I'm going to use the data that was provided by one of the groups on the Tuesday information. So if you guys are in here, thank you very much for that. Thank you. Okay, so pre-lab. First thing I did, you should have had a variable solar insulation power. Our insulation power for Tuesday was 1160 watts per meter squared. So the first thing I did was I said, okay, what's the slope of the line going to be? So I started off by using thermal energy change is mass times specific heat times changing temperature. Okay, but my incident power, but I have an incident power rather. So I'm going to divide both sides by time. So that power equals thermal energy change divided by time, which is equal to mass times specific heat times delta temperature divided by time. And that is legit as long as you do not have a phase change going on. So the delta temperature divided by time, that's actually going to be the slope of my line. And once you plug and chug it all, it comes down to this. Temperature equals 0.148 degrees C per second times elapsed time, and this 22.92, that was the starting temperature for the data. So that's your y-intercept. You graph it out, it looks like this. Shoot, going right up. Here's your actual data. I'm hoping that I see something like this in your reports. So what you should get out of this is the theoretical is much, much higher. So we did not have a super efficient collector. So question one, in 4 minutes, what's the actual energy increase in the block in joules from the starting temperature? Again, I'm going to feed energy change equals mass times specific heat times change times the delta temperature to depth in this. So it turned out to be about 5,051 joules. Okay, 5 kilojoules. Nice easy warm up. Question two, what is the average power being absorbed by the aluminum between 240 and 420 seconds? Okay, so again, average power is a change in thermal energy divided by time. So MCV delta temperature, and then I divided that by the 180.64 seconds, 11.23 watts. That's what was actually getting into the aluminum plate. Question three. What is the average heat flux power absorbed divided by collector area at that same time interval? So you had 11.23 watts coming in. It was divided over 0.023 square meters. So 483 watts per meter square. That's what was actually getting into the block. What temperature should the block have been at 240 seconds if all the sunlight was completely absorbed, remained constant, and no heat losses? Well, basically that's just come back here and look at your theoretical line at 240 seconds. So because I had an equation, I could just plug and chug. 58.44C. If your numbers varied a little bit because of starting temperature or insulation, fine. But that's what I was looking for. So what percentage of the sun's energy was captured in the collector at 240 seconds? Basically, I'm saying, what's the efficiency of the collector? So the percent captured is the captured flux divided by the available flux, 483 watts per meter squared divided by 1160. 42%. It was kind of yucky. And even when I was doing it, trying to develop the lab, I looked at that and I said, yeah, that's pretty bad. And I tried a bunch of stuff. I tried thickening up the insulation. I tried doing a double layer glass painting, and it only got worse. So I'm thinking the polycarbonate was the problem child in this. It either needed to be thinner, or maybe I needed to use actual, float plate glass or low-E insulated glass, something like that. But I'm pretty sure the polycarbonate was the problem. Okay, and then the big question in the lab, I want to take a hot shower at my off-grid camp using the absorbed power value from 240 to 420 seconds, an average main groundwater temperature of 50 degrees, which is true, standard hot water tank temperature of 140. How long will it take to heat a standard 40-gallon hot water tank to the set point? Assume the collector is 4 feet by 8 feet, just a big old sheet of plywood. The solar intensity remains constant, and the heat transfer to the water is 100% efficient. So everything that gets into the collector goes into the tank. You didn't have to make any assumptions about heat exchanger efficiency or any of that jazz. Okay, so I converted all the units. 50F is 10C, 140F is 60C. Tank volume, 151.4 liters. Collector area, 2.972 meters square. So my input power is going to be the flux times the area. So the actual power that I was gathering, 483 watts per meter square, times the area, about 1,400 watts. So 1,400 watts is going into the tank. Basically, I always think of that as like one hair dryer's worth of energy. So the density of the water, 1 liter per kilogram. We will do energy increase required. So mass times CP delta temperature. I need 31 megajoules. That is a lot of energy, folks. And we're going to revisit this idea in a later lecture, because I want you to get a gut feel for how much energy that is. That is a lot of energy. Okay, so again, really simple. Input power equals energy divided by time, or doing some algebra, time equals energy divided by input power, and when you shake and bake the numbers, time to heat the water, 6.12 hours. So I do get to take a hot shower every day at my off-grid camp. Any questions? Guys, if any of the questions were poorly worded, feel free to suggest changes. Like I said, this is my first time with this class, so if there's something that needs to be smoothed out, by all means, I'm totally open to input. Okay, lesson 6, hydrostatics. Okay, this is where we're going to talk about pressure equals rho GH. Okay, not super hard. So let's say that I'm sitting in a Los Angeles class submarine. I'm cruising along at 300 meters, 984 feet down. What's the pressure on the hull? Well, the pressure's about 438 psi. Okay, so let me tell you, that is why I was Army. Okay, when people want to poke holes in your ride home and the outside is over 400 psi, that's not a good time. I am far more of an advocate of running high. Let's swim. No, I don't do that. Okay, but Army Navy stuff aside. So, typically typically, a professor would do some kind of weirdo calculation about, you know, I have a submerged door at a certain depth, and, you know, let's calculate the centroid as some goofy shape, calculate the force on the door. Okay, that's lame. You guys can do that. I have no doubt of that. Okay, but the question that I've asked a bunch of students before is, how far up can I pull water out of a well? Now, what's the limiting factor? And a whole bunch of people had no idea what that was. So that's where we're going to go with this today. So let's say I've got a bucket of water, okay? Blue bucket of water. And I've got a pipe in there. So I want to suck the water up the pipe. There's only one reason why the water goes up the pipe goes. So you got atmospheric pressure pushing down, and as I lower the pressure at the top of the pipe, water goes up the column. I have limited my atmospheric pressure. Okay, so then right here, that pressure has got to equal atmospheric. So this pressure plus rho GH equals atmospheric right there at the water line. So let's do some math on that. So if I take 101 kPa, atmospheric pressure equal to the density of the water times G, 9.8 meters per second square. Shake and bake it, solve for H. 10.33 meters, or almost 34 feet. That is it. That is the highest level that you can suck water out of the well. What's wrong with that? Okay, remember that little demonstration I did with the bell jar? Okay, that water started to boil in the bell jar when the ambient pressure equaled the vapor pressure of the liquid. So as I start lifting that water, okay, the height of the column is going to apply more and more and more suction, just like the vacuum pump did. So eventually, I'm going to suck so hard, water's going to start to boil in the tube, and then all I'm going to be doing is sucking saturated vapor. So let's fix that. So let's say that we've got 72 degrees ambient temperature. I start sucking up my super long drinking straw. So then my pressure is going to be the ambient minus the saturation pressure equals rho GH. Okay. Throw some numbers in there. And now, at 72 degrees, all I can lift that to is 32.8 feet. So it takes off a bunch of distance. Because that water's going to start to boil. So of course, me being me, I had to actually go do it. Let's say that I'm going to suck water from a well. Maybe I want to find water for a village, maybe I want to find water for a concrete house, something like that. Lower down to that water being before I can. All right, I made that for you guys. Sorry guys, lousy audio. Before something interesting happens. Here we are on the second floor. You probably can't see it on the video, but this is 18 feet above the water line. So let's start lifting our column of water and see what happens. Okay, so there was a little bit of difference. Probably has some dissolved oxygen in the water. Fish like to breathe too. So I suspect that's where the difference came from. But I don't honestly know. It should have been spot on with the numbers. Possibly if I had boiled the water beforehand, got all the oxygen out, that might have let me get it up a little bit higher. Hydrostatics, it's not a super hard concept, guys. So I'm going to kind of leave it at that. Hopefully your fluids prof did it more justice. Okay, so where are we going from here in the class? So lesson 7, we have no labs next week. We're going to take a week off. I'm going to talk to you about some more Arduino programming. We're going to talk about interrupts. And that's going to lead us into our next lab, where we're going to play with this thing. And we're going to do a thrust-specific propulsion lab. And what I'm going to ask you folks is, number one, in the pre-lab, you're going to calculate the velocity of air required to make 1 Newton of thrust through a 7, 9, and 10-inch propeller disc. Okay, so you have to get the velocities. Then I'm going to ask you to calculate the change in kinetic energy for making 1 Newton of thrust on those 3 different rotor discs. You're going to find it's pretty different. So where we're going with this is we are going to look into why did jet engines go from, the MEE365 back in World War II that had a flow path that was like, 18, 24 inches in diameter, pretty similar to the F-15's flow path. But now we got GE90 engines that are pushing 9 feet in diameter. Why did you do that? Okay, we're going to actually look into the physics of why that works. So this little gizmo that I made, it's kind of fun. It's got a load cell right here, so we can actually measure the real-time thrust going in that direction. And it has a full dynamometer up here. So this load cell will give you the real-time torque of the motor. There's an electric photosensor in the front, right here. So we're going to shine a laser into that, and we're going to time the blade passing to get the rotation. So if we know the RPM, we know the torque, we can get the actual shaft power coming out of that motor. And we can look at, okay, how much energy am I putting in, how much energy is coming out, what did it actually cost me to make that thrust, so we can look at propulsion efficiency. We're going to look at all of that jazz as a function of propeller diameter. And by the end of it, you can have a really good idea of why we went from low bypass engines on the MEE365 to the GE90s that are like 9 feet in diameter. We're going to have to talk about a whole bunch of stuff, so I'm not going to leave you out in the woods. We'll go over all the load cell stuff, the electric eye stuff. This time you're going to have to do a little more programming. So you're going to have to add a second analog read function to your MEE365 template. I'm going to go over interrupts for timing. That's a little bit of an advanced thing, but it's not bad. Okay, I'm going to spoon feed you that one. And then you should be good to go. So that will be coming up after we have our little fall break. That's it, guys. That's all I got. Any questions? Going once? Going twice? Have a great weekend.